Okay, in this video, we will still be talking about alcohols and phenols, chapter 3, but we will now go into the physical properties of alcohol. Okay. So first, we're going to talk about boiling temperature. So boiling temperature of alcohol generally is higher as compared to alkanes of similar molecular mass. What does it mean by this is that, for example, we have ethane and ethanol. So in terms of boiling point between these two compounds, they have the same number of carbon atoms, okay? Same number of carbon atom, but of course hydrogen is different, okay? They are different in terms of their structure, okay? So both have 2 carbons. The only difference now is that ethanol will have the OH, okay? The presence of OH, okay? So between these 2 components, due to the presence of the OH group, okay, due to the presence of the OH group here, okay, so hence the boiling temperature would be higher as compared to its corresponding alkane of similar molecular mass. Alright, in the case of alcohols, there are hydrogen bonds. So when we have the OH here, the hydroxyl group, this will form hydrogen bonding with one another, okay, or with other water molecules, okay, or with other it can be water molecules. As long as it can form hydrogen bondings, then it will form the hydrogen bonding among one another. All right, so in the case of alkanes, there's only intermolecular forces, which is the van der Waals forces. So hydrogen bonds are much stronger than van der Waals forces. So because of this particular reason, whereby the presence of hydrogen bonding is stronger than the van der Waals forces, hence why the boiling temperature is much higher for alcohol. Okay, so I just want to add on. In terms of boiling temperature, we have the alkene. Okay, so here we have alkane and then we have ethanol, and also alcohol. Sorry, so alcohol. So sometimes you can't forget your carbonyl groups as well. We have the ketones and the aldehydes. Okay, so even though ketone and aldehyde, they have the C double bond O bonding here, but right, let's draw this as accurate as possible. Okay, so even though in the carbonyl group here we have this, all right, this will have, of course, hydrogen. It can also form hydrogen bonding, but because it's only just oxygen, the hydrogen bonding that it's formed is not as strong as the alcohol. All right, and then another one we're going to combine is that carboxylic acid. So for carboxylic acid should be the highest. Why would it be the highest? Because not only does it have the C double bond O, it has the OH attached. Okay, so in terms of boiling temperature, it follows this particular sequence. All right, if we're talking about the corresponding compounds of similar molecular mass. All right, now let's move on to solubility. So among all the organic compounds, alcohols are among the most soluble compounds. Why? Because solubility here, we're talking about soluble in H2O. So in order for it to be soluble in H2O, of course, it must be able to form hydrogen bonding, right? So because of this, all right, because of the OH group in the alcohol, hydroxyl group, the presence of the hydroxyl group is the one that will form the hydrogen bonding with the water molecules, hence increasing solubility. So alcohols, if they are small in size, meaning to say 1 carbon, okay, we have the methanol, all right, or you have ethanol, or you have ethanol, or if you have propanol, these are considered small carbon. Up to about 5 carbon is considered quite small. So up to 5 is about pentanol. Okay, or pentanol, hexanol. These are considered still quite soluble. Okay, but as the number of carbon atoms increases, all right, as the number of carbon atoms increases, it becomes a bigger alcohol compound, right? So as the number of carbon atom increases, it will decrease its solubility. Okay, so more of the molecule is non-polar carbon chain. So the only part of the alcohol compound that is polar is actually the hydroxyl group. So the remaining areas are non-polar. So when they are non-polar, they are not very soluble in water. Okay, maybe some will be soluble in certain extent, but again, it will be resisting solubility in water. So less attraction of polar water molecules, okay, will reduce the solubility. So if you're going to explain on the solubility of alcohol, you can use the same reason as the boiling point, whereby the presence of the hydroxyl group. Okay, so here are some examples for where we show you the hydrogen bonding. So this is between two molecules, two compounds that are of the same build-up, okay, or same or different. As long as they have the OH, you see, they're bound at the OH. So this is the part that forms the hydrogen bonding. Okay, so when you have the hydrogen bonding, okay, so I hope you still remember what's hydrophobic and hydrophilic. So hydrophobic, basically, in simpler sense, it means it's afraid of water, right? Afraid of water. But if hydrophilic means it's friendly, right, with water. So if that's the case, this is the only part that's soluble in water, whereas this remaining part is hydrophobic. So hence, as the compound gets bigger and bigger, the solubility, okay, solubility will decrease. So here we can say that the size of the alcohol, as it increases, the solubility will decreases. Okay, so here are some self-tutorial. You can try and rank these compounds in terms of their increasing boiling point and also the water solubility. And then next on, you can also try and explain. Okay, try and explain. Now, of course, it's self-tutorial. Later, you will find the answers. You can actually get the answers from me, okay? Or I will. we can discuss it during class as well. Now, we're gonna go into the second last part, which is the synthesis of alcohol. So synthesis of alcohol, we have discussed it before when we were talking about alkenes, okay, haloalkanes and ketones and aldehydes. Okay, so we can synthesize alcohols from alkenes, haloalkanes, and carbonyl compounds like aldehydes and ketones. Okay, so for the first one, we're talking about acid-catalyzed hydration of alkene. Acid-catalyzed hydration of alkene. So this is from alkene to alcohol. Alkene to alcohol. Alkene to alcohol. So what is the substance used here is we need acid catalyst. So acid catalyst hydration. So meaning to say we need water and then we need an acid to catalyze the reaction. So the reagent here would be H2O and H2SO4. Okay, so we're using concentrated acid. Okay, now when you include water into the compound, especially the alkene, make sure you still remember the Markovnikov rule. Okay, where we talk about the rich get richer, means the compound that holds more hydrogen will attach the hydrogen, whereas the one that has the lesser hydrogen will attach the OH. Okay, so I hope you still remember this. If not, please refer back to chapter 2. Okay, another way to synthesize alcohol is using the hydrolysis of alkyl halides, or hydrolysis of alkyl halide. Okay, so alkyl halide here is actually a haloalkane, right? A haloalkane. So here this is a haloalkane. Okay, haloalkane. So we have a haloalkane to alcohol. So what do we need here? we will be using, again, a strong hydrolysis means we need water, so definitely we need H2O, and then we need a strong alkaline, okay, so calcium hydroxide in the presence of a little bit of heat. Okay, so this is one synthesis method, two synthesis method. Okay, one synthesis method, two synthesis method of alcohol. Right, so preparation of alcohol from alkyl halides are two steps mechanism. It is also known as a nucleophilic substitution reaction. Okay, so alright, there are two steps mechanism here. Now we're not going to go into detail in terms of the mechanism, so you can skip this part. Alright, so preparation of alcohols can also be from aldehyde and also ketones. Now this is where you have to be careful. Aldehydes will give you primary alcohols and ketones will give you secondary alcohol. And your reducing agent here, of course, is not something new. What we always use is lithium aluminum anhydride, or there's another option is sodium borohydride. Okay, so aldehydes to primary alcohol. So another catalyst that it must go together is with diethyl ether. Okay, so the reduction here, all the reagents used is lithium aluminum hydride and diethyl ether. Okay, and then here they also have water. So you just follow. Now if you're using sodium borohydride is simpler, whereby it's just sodium borohydride and ethanol. Okay, so these are the reagent for reduction. Right, reduction. Okay, so reduction. Again, aldehydes will give you primary alcohol. Ketones will give you secondary alcohol. Unconjugated double bonds. For example, like this one. Okay, like this one, no reaction. Means like this one, it has no reaction. So in the product later, this part is unaffected. The only part that is affected, is this part. Okay, so please be very careful. Alright, be very careful. This is actually from a ketone to our secondary alcohol. Okay, so next we have the reactions of alcohol. So reactions of alcohol, one of it is that for phenol or even any alcohol, you can react it with sodium and it will form a salt. So why do we say it's a salt here? Because, okay, the O stays to the compound, but the hydrogen here will be removed to form hydrogen gas, and the H will be replaced with sodium. Okay, another substance that can use is also sodium NH2. Okay, sodium NH2, and the side product will be NH3. Okay, so this can happen not only on this can happen only on alcohols. Okay, so don't confuse, this is not a phenol. Okay, my bad, this is cyclohexanol. Okay, so this is still everything is the same except now it has become an ion. Okay, next we have the reaction of hydrogen halides. So if you have alcohol reacting with hydrogen halide, alright, you will get a alkyl halide. So means alkyl halide is also known as a haloalkene. So this is one way to synthesize a haloalkene, or one of the reactions from alcohol to haloalkane. So if you remember earlier on, your haloalkanes, you can use haloalkanes. Okay, alkyl halide is haloalkane also. Haloalkane, you can synthesize alcohol, but at the same time, your alcohol can also be used to synthesize the haloalkane. So what reagents you use? Very simple, just a hydrogen halide. So the hydrogen halide is added in, reacted, and then the halide will substitute with the OH, the hydroxyl group. It will be replaced, replaced with the hydroxyl group, and then your side product here will be H2O. Okay, another reaction that alcohol can go through is acid-catalyzed dehydration. So dehydration here means we are removing H2O. So your product should have water. So if we're going to remove H2O, okay, then we'll also be removing another H to form the H2O, right? So remove the OH with a H to get the H2O, you will get an alkene. So earlier you have your alkene can be synthesized to give you alcohol. Now you have a reverse reaction whereby your alcohol can be used to synthesize alkene, the reverse. So of course the reactant here is a bit different already. Okay, so please take note, this is the reagent. This is the reagent for acid-catalyzed dehydration. Okay, so potassium hydrogen sulfate. Okay, potassium hydrogen sulfate. Now for hydrogen halide, you just add the halide here. Okay, so take note of the reagents used, because this is the ones that it's important that they will ask. Okay, and of course your final product, how does it affect? Once you remove the water, then you get alkene, so there should be a double bond here. Alright, let's move on. Oxidation of alcohols. So just now you have alcohols being from aldehyde and ketone. So aldehyde, ketone, we can get alcohol by reduction. So the opposite of reduction is oxidation. Right? So oxidation of alcohols. Okay, if you are dealing with primary alcohols, your product, okay, your final product, okay. Now we're talking about strong oxidizing agent. Your final product for primary alcohol would be a carboxylic acid. Carboxylic acid for primary alcohol, because these are very strong oxidizing agent. So when we are using strong oxidizing agents, okay, and we are dealing with primary alcohols, okay, hope you remember what is primary alcohol. So your aldehyde here is an intermediate. Okay, it doesn't stop at aldehyde. So we have to remove this. Okay, so the reverse reaction. So if we oxidize alcohol or primary alcohol, we're going to get carboxylic acid as well. So this is one of the way to synthesize carboxylic acid. Okay, it will not stop at aldehyde if you are using strong oxidizing agent. Strong oxidizing agent here, we're talking about chromic acid. Okay, whether if it's using this method, using this reagent, or using this reagent. Okay, or if you want to use this reagent, also can. These are all strong oxidizing agents. These are all strong oxidizing agents. Okay, now what if you want to get aldehyde? Okay, later on, the next slide you'll see. Yeah. Another thing we need to highlight in this slide is that tertiary alcohols, no reaction. So if you use even strong oxidizing agent, if it is a tertiary alcohol, okay, if it's a tertiary alcohol, there is no reaction. Please take note, okay, no reaction. Secondary alcohol, you can stop at ketone, right? It will give you a ketone. But primary alcohols, please be careful. Your aldehyde, if you're using strong oxidizing agent, okay, strong oxidizing agent, your final product will be a carboxylic acid and not an aldehyde. Okay, this is using strong oxidizing agent. Okay, so these are all strong oxidizing agent. Look at the combination here, strong oxidizing agent. Right. Now, if we want to stop it at aldehyde and ketone, there is a way to stop it. Okay, seems like we're missing here. Okay, there is one way to get the aldehyde. I'm sure if you refer back to your if you refer to chapter 4 later on in carbonyl compounds, yes, you can get aldehyde from primary alcohol. How? You have to use a different type of oxidizing agent, which is called the PCC or PDC or PDC. I hope you still remember this. Okay, if you want to get your final product as aldehyde from a primary alcohol, then you have to use a different type of oxidizing agent. If you are using a strong oxidizing agent like dichromates, okay, or the potassium permanganate, your final product will be carboxylic acid, okay, and not aldehyde. So for you to synthesize aldehyde from alcohol, you have to use a different type of oxidizing agent. Please take note on that. But if it's a secondary alcohol, then there's no issue. If you're using strong oxidizing agent, you will still get a ketone. If it's tertiary alcohol, no reaction at all. Please take note. Now, phenols. Okay, so phenol is a derivative. We call it a derivative of benzene. Okay, so a derivative of benzene. Like benzene, it can undergo nitration or nitration, sulfonation as well. Okay, but the type of reactions that phenols can undergo is far more as compared to the benzene ring itself only. Why? Because remember we talked about the reactivity of phenol is very high, is higher compared to the benzene. Okay, compared to benzene. So for nitration, alright, we're still using the same reactant, but if it's phenol, alright, the reaction doesn't stop at just auto or para, okay, because HNO3 is an indicator of concentrated nitric acid. So if you're using concentrated, then your product will be a polynitrate phenol. So here this is a 2, 3, 4, 5, 6, 7. So 2, 4, 6 trinitrophenol. This is the product name. Okay, if you're using concentrated nitric acid, you'll get 2,4,6 trinitrophenol. But if you want to get an ortho nitrophenol, okay, or a para nitrophenol, then you use dilute nitric acid. Okay, why is it auto and para and non meta? I'm sure you still remember effects of the substituents. So here the substituent we're talking about is the hydroxyl group. So hydroxyl is auto and para directing. So hence why the product is auto nitrophenol, para nitrophenol. Okay. Next we have halogenation. Same thing. It can undergo the same reaction as the benzene ring, but if it's just bromine, aqueous bromine, you have a polyhalogenation. Again, 2, 4, 6 tribromo phenol. Now if you want to get an orthobromophenol or a para bromophenol, you have to use with CCl4, a non-polar solvent. Okay, so if this combination, if you want to get these two, if you want a polyhalogenated phenol, then you just use the bromine. So be very careful. Sulfonation, same thing. But for sulfonation, there's no polysulfonation here. Now, the difference between these two is the temperature. So at lower temperature, we get the auto position. At 100 degrees C, we get the para position. Okay. So at low temperature, reaction is non-reversible and low activation energy. This is activation energy. Alright. Higher temperature reaction is reversible. A more stable para product is formed. Okay. Then we have the Fredo Alkylation. So phenol can also undergo Fredo Alkylation. Alright. So this is auto para, right? Auto para. But why is the product only para? Simply because of stability. Okay, if it was in the para position, then it would be a big chain here. So what happens is that these two will repel one another and it will become unstable. So when it becomes unstable, it will try to find a more stable position, so it will go to para. So this one will only have one product due to stability. Okay, and then we have Fredo acylation. Same thing again, same issue here. We only have one product. There's only one product, whereby the alkyl, this compound, okay, will be at the para position due to stability. It is more stable in the para position as compared to the auto position, whereby the two structures will be very near to one another and then it can repel. So when it repels, it becomes unstable. So when it becomes unstable, it will try to find the most stable position, which is the para position. So here they say, do not confuse Fredo acylation with esterification. So this is very different, very different. This is based on, this is acylation. Look at the, you have to look at the reactant and also you have to look at the reagent used. Okay, for esterification is a bit different. Okay, then we have nitrosation. Okay, so again, same, you only have one product here, one product. Why? Para is more stable. Okay, so para is stable. Very weak nitrophile. Okay, this one also the same. Okay, para position. Okay, one product. Diazonium salts. Okay, so phenols can couple with diazonium salts. So this is a diazonium salt. Okay, salt, chloride. Chloride is a salt, right? So what happens is that, again, the same thing between these two substituents, which will be, okay, both are auto and para. So if we follow OH, auto is here, para is here. If we follow CH, auto is here, para is here. Okay, so between the alkyl and the phenol group, OH will have a more priority, hence why the position is at the para position. Okay, so it will combine here at the para position. Then we have the Colby reaction or carbonation. Okay, so this is a sodium, this is a salt, react with CO2, we got sodium salicylate, we get salicylic acid. Okay, salicylic acid. So H plus, normally here we're talking about acid. Okay, acid. H plus, normally we're adding acid. Okay, so that is all for chapter 3. Okay, so I see you in the next topic again.